Okay, what I'd like to do over here is to briefly review the issue about low cell counts. Let's say that we're dealing over here with schools and students. And we've said that overall the event rate is 0.5. There are, let's deal with the control group, there are 20 students within each school. If there are 20 students and the event rate is 0.5, the expected number of events in each cell is 10. But we're not dealing with a single 2x2. We're dealing with a series of 2x2. We have to look at this within schools. And while on average the expected number of events is 10, in any given school we might expect fewer than 10 events or more than 10 events. Based on distribution theory, we can say that there are going to be less than 1% of the schools is going to have an actual event count of less than 3.5. So that's not a problem over here. If we expect the prevalence is going to be lower, let's say the prevalence is 0.4, then we still have less than 1% of the schools presenting a problem. With the prevalence of 0.4, it was still less than 1%. With 0.3, we would expect that about 7% of the schools would have an observed cell count of less than 3.5. When the prevalence is 0.3, if we have 20 students in the school, the expected number of events is 6, and 7% of the schools are actually going to have less than 3.5. If the prevalence drops to 0.2, then the expected number of events is 4, and it should therefore be intuitive that a decent proportion of them are going to have cell counts of less than 3.5. In fact, if we set the event rate so that the expected number of events is about 3, and a half, you can see that about half of the schools are expected to have cell counts of less than 3.5, which of course makes perfect sense. Let me bring this back to 0.20. So if we actually have a prevalence of 0.2, the problem is that we're going to have a lot of cells with less than 3.5 events, and that's probably a violation of the assumptions. The only thing we can do in that case is to increase the number of students, and you can see that at some point that's no longer a problem. In this case, if we bring it up to 29 students per condition, 29 with the expected number of events is 0.2, gives us an expected number on average of 5.8 events, and less than 10% of the schools are going to present a problem of having too low of a cell count. Let's bring this back up to 0.25 for a minute, so that in this case only about 2% of the cells are expected to have a problem. The second way that a problem arises is if the prevalence varies from school to school. We were dealing a minute ago with a situation where all of the schools had a prevalence of 0.25. But if we start allowing the risk to vary from school to school, let's say we have a span of 0.20, that means that the risk is going to vary from as low as 0.15 in some schools to 0.35 in others. Obviously, the schools down here are going to have a greater likelihood of having a cell count that is less than 3.5. So when the span of this was 0, only 2% of the schools had an expected problem. If the span goes up to 0.20, then 4% of the schools have an expected problem. And if the span goes up to 0.35, at this point more than 10% of the schools have an expected problem. And therefore, again, we need to increase the number of the number of students per school to get rid of the problem. The last issue we need to deal with is, so far we've been treating this as though the odds ratio was 1.0, which means that the problem is going to be the same for the treated group and the control group. If we bring the odds ratio down below that, let's say we bring the odds ratio down even to 0.9, then while we did not have a problem in the control group because the expected event rate was 0.25, we do in the treated group. The expected event rate is 0.23, or to make this a little bit more plausible, let's set the odds ratio at 0.7. So the expected event rate over here is 0.18, and therefore the expected number of events is smaller, and therefore the proportion of schools that are going to have a low event count in the treated group is now 21%, which again is a problem. There are two ways that we can deal with this. One of them is that we can simply increase the number of students overall, or if we wanted to be a little bit more refined, we could set the number of students in each group separately, and all that we need to do here is to increase the number of students in the treated group because that's where the problem was. So that's the basic idea over here, is we need to be sure that the proportion of cells with a low cell count does not exceed 10%. As I emphasized in the materials, this is a tentative number. It's not clear that 10% is going to cause a problem, and it's not clear that numbers above 10% are safe. It's also not entirely clear that 3.5 is the number that we should be using. So all of these data are preliminary. Obviously, the smaller the proportion of problematic cells, the more likely it is that you're going to be okay. The higher the number of problematic cells, the more likely it is that you're going to have a problem. And we've set 10% as a plausible number based on some preliminary simulations that we've run. This is going to require a certain amount of research in the future, and people are encouraged to do that if they want to. The other issue I dealt with this week is the issue of setting delta. This is actually a separate issue. It's related in the sense that both of these problems come about when we have low expected risks. So they're related in that way. They really are, though, two somewhat different problems. The problem of delta is what happens if we have a large span of risks. I'm going to get rid of this. We've sort of dealt with that already. Let's turn that off. So that the mean prevalence, let's say, is 0.2, but we also have a span that is wide enough so that in some of the schools, the expected risk is going to approach 0. The problem is that the way the analysis is done, you can't actually have 0 as a risk rate. It has to be something greater than 0, or the algorithm simply stops working, since this is done in the logit metric, and you can't actually have a 0 event rate. You can get very close to 0, but you can't actually reach it. So what do you do about that? Well, what we do in the program is when something butts up against 0, we set it to some value slightly higher than 0. And by default, that value is going to be 0.001. And when this warning over here pops up, the first thing, this is really meant as a diagnostic, the first thing you should say is, wait a second, do I really expect to have schools where the event rate is approaching 0? And in some cases, the answer is going to be no. Let's say we're talking here about dropouts. I've never seen a school where the dropout rate in high school is less than 5% or less than 2% or whatever the number might be. If I've set this up in such a way that the dropout rate is approaching 0, then I really need to go back and rethink my numbers. Either the prevalence that I've set down here for dropouts is too low and I need to increase that, or the span that I've set is too high and I need to decrease that so that this problem over here disappears. So that's really the first thing that you should be doing. In some cases, for example, people dealing with medical issues, let's say with adverse events or something of that sort, might actually have a situation where in some hospitals the risk of the event really will approach zero. And then the question is, what if something butts up against zero in the way that we have set up this study? What do you want to do with that? And you have to set this value called delta. And what happens then is if the in any cell where the risk appears to be zero, the program is going to set the risk at some number. In this example, it's going to set it at 0.001 rather than zero. And we can set this at 0.001 or at 0.01 or 0.0001. And the way to set that is to say, well, if the population that I'm dealing with, I really never expect to see a risk less than 1%, then you could set that at 1%, 0.01. And any cell that is less than 1% is simply going to be set at 1%. If, on the other hand, you say, there really are hospitals where the risk might be as low as 0.001, then that is where you should set it. And if it's 0.0001, that is where you should set it. The point that I tried to make in the materials is that this actually has a very important impact on power in two ways. The first way is that if we allow risks of 0.0001, that is a much broader range than allowing them to go down to 0.001 or 0.01. While these differences appear to be very small in the raw metric of proportions, the difference between 0.01 and 0.001 is obviously trivial. In the logit metric, these are very large differences. So if we allow this to as this gets closer and closer to zero, what we're saying is that the variance of the risks is much higher, and therefore the impact on power is going to be substantial. As you go closer and closer to zero, power is going to get lower and lower. It also has a secondary impact, which is that as the risks get closer and closer to zero, the number of cells where the expected event rate is going to be low will increase. And they'll increase substantially, which means that the smallest number allowed per cell is going to get larger. So let's